We're always looking at the cutting edge of renewables. And, well, today's idea sounds almost like science fiction, getting electricity not just from the sun, but from rain.
Yeah, it's pretty out there.
Can we actually capture useful energy from, raindrops hitting a panel?
That's exactly the question. And our deep dive today zooms in on a white paper from Black Knight Power. They're exploring this innovation, specifically looking at Maryland in the U.S.
Maryland, okay.
Yeah, so our mission here is really to unpack the tech, look at Maryland's climate, the costs, and, what this could actually mean in the real world for you.
Okay, let's definitely unpack this. It sounds fascinating. I mean, solar panels, most of us get that. But rain-powered, how did that work?
It's really clever stuff. These aren't your standard solar panels. They actually integrate something called Triboelectric nanogenerators, the TNGs for short, right alongside the normal solar cells.
Energies.
Think about static electricity, like rubbing a balloon on your hair. That basic idea, the triboelectric effect. TNGs capture that friction-generated charge, but on a microscale.
Ah, okay.
So when raindrops hit this special graphene-coated surface, graphene is super thin, conductive carbon, the positive ions in the rainwater interact with the electron-rich graphene.
And that generates electricity.
Exactly. Through what's called liquid-solid contact electrification, it's the physical impact and charge difference doing the work.
So the raindrop hitting the surface creates a tiny charge. Sounds intricate, but efficiency-wise, how much we're really talking about per drop?
Well, that's the kicker. The panels, the hybrid ones, can still get up to, say, 6.53% efficiency from sunlight, which is, okay. But the energy from each raindrop, it's minuscule. We're talking picowatts.
Picowatts, wow. Okay, for you listening, what does that actually mean? Can picowatts power anything?
Right, good question. Context is key. A single LED light needs milliwatts. That's thousands, maybe millions of times more than a picowatt.
So, not charging your phone with rain anytime soon.
No, definitely not directly with rain alone, not right now. It's more proof of concept, really. Maybe for ultra-low power sensors or like a tiny, tiny boost to the solar output.
Okay.
But it shows the huge challenge in scaling this up for, meaningful energy harvesting. And durability is another big question mark with these sensitive materials out in the weather.
Right, durability. So if the output per drop is so small, what's the bigger picture? And why focus on Maryland? What's special about its climate?
Maryland's interesting. It gets pretty diverse weather. You've got over 250 sunny days a year, great for traditional solar.
That's a lot of sun.
It is, but it also gets moderate rain all year round. And crucially, Maryland is in the path of Atlantic hurricanes, June to November.
Ah, hurricane season.
Exactly. They're forecasting up to 5 major storms for 2025. Category 3 ones over 111 miles per hour. Think about the potential for blackouts.
Okay, now I see the connection.
That's where even a little bit of rain power could potentially be, really important.
That makes sense. So, beyond just generating a tiny bit of power, how else do these panels complement the solar side, especially in a place like Maryland?
Well, there are a few interesting synergies. First, the rain actually cleans the panels, washes off dust and grime.
Oh, that's handy. Improves the solar efficiency.
Right. And rain also cools the panels down. Heat can actually reduce solar panel efficiency, so cooling helps mitigate that.
Okay, cleaning and cooling makes sense.
But here's the really compelling part for places like Maryland. These things could generate some power during storms or just on overcast days, supplementing output when sunlight is low or gone completely.
So it's about resilience, filling the gaps when solar isn't working well. That could be huge. But hurricanes again. If you've got these complex panels, how do they hold up to those kinds of winds and debris? Is durability a bigger issue than just normal wear?
That's a really critical point. Durability in extreme weather is absolutely a major focus for R&D. They need to withstand the forces, not just collect the drops.
Okay, so what about costs? You mentioned traditional solar is fairly competitive in Maryland.
Yeah, traditional solar installation there runs about $2.59 to $3.50 per watt, roughly 10% cheaper than the national average. So it's already a decent market.
But this new tech, I'm guessing it's not cheaper.
Oh, definitely not yet. It's still very much in development. There's no real commercial pricing. Costs are TBD, but they'll almost certainly be higher. R&D is expensive.
Right.
And we can look at real-world tests, like in Shenzhen, China. Researchers there built hybrid panels. They did see high instantaneous power spikes during rain. So the concept works, But continuous power generation, that's the big hurdle, mostly because of something called coupling capacitance. Basically, it's hard to efficiently grab and store those tiny intermittent bursts of energy from each drop.
So the potential is there, but capturing it reliably is tough.
Exactly.
Yeah.
That's the tension. You've got this promising idea, but the efficiency per drop is low, the costs are likely high, and continuous output is tricky. Can we bridge that gap? That's the big question.
So wrapping this up, what does this all mean for you, our listener, and for places like Maryland?
Well, I think the main takeaway is that this kind of rain-powered tech could seriously boost energy resilience, especially during storms, cloudy days. It complements solar.
But it's not a replacement.
No, not at all. And the costs are still a big unknown, likely higher than regular solar for a while. Plus, durability and scaling up need a lot more work before this is, widely usable.
So lots of research needed.
Definitely. But connecting it to the bigger picture, it's about making our energy systems tougher, more adaptable, especially with changing climate patterns.
Which leaves us with a pretty provocative thought, doesn't it? Could a place like Maryland, with that specific mix of sun and storms, actually lead the way? Could integrating rain power be the key to a more resilient energy future, not just there, but in any region facing unpredictable weather?